Hi, today we're going to see a bit about modeling and estimating model parameters using SciPy for fitting, also NumPy. I'm also going to be shifting a bit from the basics of the programming language of Python to focus not only on these libraries, on these tools, but also on more sophisticated algorithms that you can use to help process your data. So on this first hour, we're going to look at integration, how to solve differential equations for modeling dynamic systems. And I'm going to give a few examples, the SIR model for epidemics and chemical reactions. And then using the SciPy library also to adjust parameters. So both of these will be with tools from SciPy that you can use to solve these kind of problems. And the emphasis here, although I'm going to be talking also about the code, how to implement this in Python, but the emphasis now is a bit more on learning what kind of tools you have available and what kind of things you can do with these tools and with programming that you would not be able to do with spreadsheets or without programming. So especially for these 2 weeks, this lecture today and next week, I'm going to focus on what you can do with programming that allows you to go beyond what you did so far without programming. So let's look at this problem of doing numerical integration. So just a very basic introduction. We suppose we have some function. I'm representing it here with this red line, and we want to integrate the function in this interval between 0 and 6. So we can do this numerically by splitting the function into slices, small slices, computing the value of the function at the center of each slice, and then adding the areas of these slices. So this would be a very simple and naive algorithm for computing the integral of a function. There we're going to use things that are a lot more sophisticated, but this gives you the general idea. If you can evaluate the function, you can use this evaluation to compute the integral numerically. So basically, if we have the derivative, we can get the function because the integral, this function is the derivative of this integral here. And this is the basic idea for solving differential equations or systems, dynamic systems that we can describe with differential equations. So let's take this SIR model. This is a compartmental model for epidemiological modeling. It's a very basic model. Usually epidemiologists use more sophisticated versions of this. But basically we have this S, which is the people who are susceptible to the disease, so the number of people who can catch some disease. We have the I, which are the infected people, those who carry the disease and can infect others. And then we have the R, which are the recovered, those who had the disease and no longer can catch it. So they are now immune to the disease. And the idea is that people who start in the susceptible group, they can catch the disease, become infected, and start infecting others, and eventually they recover and no longer infect or are infected by others. And we can describe the flux between these different compartments, these different states, with a set of 3 differential equations. So the variation of the susceptible population over time is equal to how many people are infected at each time step, so at each instant. And we can assume that there is some parameter, this delta, which is which measures the probability of infection, of someone becoming infected in contact with an infected person. And then the probability of a susceptible person having contact with some infected person will depend on the proportion of infected people in the population. So this I, the number of infected people, divided by n, the total population size. So this gives us how the number of susceptible people is changing over time, depending on how many susceptible people there are. The more there are, the more can be infected, and the proportion of infected people multiplied by that delta. And this has a minus sign because when susceptible people get infected, they stop being susceptible. So we reduce the S compartment and we increase the I compartment. So conversely, the infected population will increase in the same rate as the susceptible population is decreasing. So this is the same expression apart from the minus sign. However, infected people can also recover. So we have here this recovery rate. This is a probability of recovering, or the fraction of people who recover in each time unit. For example, each day, each week, whatever we use for our units. And this will decrease the number of infected people. And this is what increases recovered. So recovered start at 0, and then once infected people start recovering, the recovered compartment will start filling up. So these are the three differential equations that model how in a population people change from susceptible to infected and infected to recovered. The way we can integrate these equations in order to compute how many people are in each state at each time, one simple approach to this would be Euler's method, which is let us consider a very small time step. So this should be an upper case delta, not a lowercase, but a small time step delta t, where the step is small enough so we can assume that the derivatives are constant in that interval, so approximately constant. So in that case, we can compute the value of one of these variables in the next time step, starting from the value on the current time step and then multiplying the time step by the value of the derivative. So if we assume that the derivative, this f here, is constant within this time step, because the time step is very small, we just compute the value and add to the previous value. So this is similar to what we were doing here with the slices. We assume that the function in this interval is approximately constant like this, so we add each slice. And if the slices are small enough, the error can be very small. In practice, this is not a good method because you would need very small time steps for this to converge and to be accurate. So usually what the algorithms do is use some version, usually a lot more sophisticated version of the inverse, the backward Euler's method. So the idea is the same. We are taking a small time step. We are computing the value of one of these variables after this time step, but we are taking the value of the derivative at the end of the time step. Now, this is a bit tricky because we need to have the value of the variables at the end of the time step to compute the value of the derivative at the end of the time step. So this requires solving for this unknown here, which is what will be the value after the time step. So computationally, these are more complex methods, but they converge faster, and these are what are actually implemented and we're going to use. However, these details fall a bit outside the scope of the course. I just mentioned this because you have lots of different algorithms and they can respond differently to different types of systems, whether they are stiff or not, and what kind of problems you may have when modeling your own system. So if this works just out of the box, you don't need to worry too much. If you have some problems because of some numerical aspects of your system, you need to dig a bit more into the algorithms and figure out what is the best one for your particular model. But for this simple one, we don't have to worry about those things. So let's use the SciPy library. We're going to use the integrate module, and this has this function for integrating ordinary differential equations. So this sort of equations we are going to use to describe this model. And the argument you give to the integrator, this function, is a function that returns the derivatives. So the first thing we need to do is to create a function that returns the derivatives given the values of our variables. So what the int function will do is to call the function that outputs the derivatives in order to compute these different values and to solve these equations for the integration. So this is the start of our script. We're going to import what we need, NumPy, and from SciPy integrate we're going to import this int, the function to integrate differential equations. We're also going to do plot, so we import matplotlib, and this part here is a matter of taste. If you want to use some style, if you don't, you can just omit it and you leave the default. So now what we're going to do is write down these equations in a function. The function must have this format. The first thing that we're going to, the first argument here is going to be an array with all the variables we are integrating, with respect to which we are integrating. So this would be an array of 3 values with S, I, and R. We could use the vals variable and use vals 0, vals 1, and so on, but this is a bit risky because it makes it easier to make mistakes. So I recommend, when you're doing this sort of things, to do something like this. Use Python's unpacking, and so we're going to unpack the 3 values into 3 variables that make the codes easier to read and so harder to make mistakes. We also need, so the other thing that int is going to send to give the derivative function, the one that computes the gradient, is the time at which we are. In this case, we don't need the time, but we need to have it there as a parameter too, because it will be sent to this function. Everything else, we can have whatever we want, because then we can give that to int just to pass to the function. So in this case, we need the total population size and the 2 parameters of our model, beta and gamma. So these are the probability of becoming infected and the probability of recovering at each time unit. So here is just the expression. So the derivative of S, the susceptible population with respect to time, is minus beta Si divided by n. So this is basically our first expression here. Then we have the same thing for I. So this is just the symmetrical of that one, minus gamma I, because these are the ones that recover at each time step, and the recovered is just gamma I. So these 3 values, the S dt, the I dt, and the R dt, are the derivatives with respect to time of all these SIR variables, and we return the 3 of them. So we receive the 3 and we return the 3 derivatives in the same order. So once we have this function, now we can just plug it into the int function. So this is our gradient function. This is the function to compute the values for the model. So let's say we have some a vector of time steps we want to compute in. We have the parameters beta and gamma and the parameters for the population. This one I left with defaults. So we're going to start our simulation with 1 infected person, no recovered persons, and a population size of 10 million. So this would be for Portugal. And here we have the 3 starting values. So S is the total population minus those that are infected and recovered at the beginning. I is the initial value of infected, it's one person, and R the initial value of infected. So these parameters here with default values, we can omit them, or if we want to use the function in different conditions, we just put in different values as we want. So this is the starting condition. This t is a vector with all the time steps for which we want to compute the SIR values. And now we're going to call the int, the function to integrate the differential equations, and we're going to give it as a first argument the function that outputs the gradients. Notice that we are not putting here parentheses or anything after this, because we do not want to execute the function at this point. We want to give the function object to this one, to int, so that it can call the function whenever it needs. And then we give it the starting values for SIR, the values of t, this is a vector, the time steps for which we want to compute the SIR values, and any additional arguments we want to have here after the time, the current time when the function is called. So basically int will ignore these parameters and just send the values directly to the gradient function. This is one way in which you can have your gradient function access other variables that int doesn't care about. And now we return the results, and so we can test this. Let's create 1 year of weeks, so from 0 to 52, but we want to compute the SIR values in 1000 points uniformly distributed in those 52 weeks. Now we can create gamma, so let's say we are looking at this new coronavirus, so basically the time it takes to recover is about 2.5 weeks, so 18 days or something like that on average. Since we are using weeks as the unit, gamma is the probability of recovery per week would be, or the fraction of infected individuals that recover per week, so it's 1 over 2.5. Beta is the fraction of individuals that infect others, assuming that everyone is still susceptible. This will reduce as more and more people already become infected, but so this we can obtain this from the R0, which is the number of people on average each individual will infect, and multiplied by the probability of recovering, so or divided by the time it takes to recover. So basically we are using a disease that has a recovery time of 2.5 weeks, and on average each sick individual will infect 3 others. So this is basically approximately the parameters for COVID-19. So now we call the function to compute the SIR. We give the time steps that we want computed and the 2 additional parameters. These others we leave by default. And now we get a matrix with 1000 rows, because we asked to compute for all these time steps, and 3 columns, each one corresponding to S, I, and R. And this tells us how the values evolve during the disease. One thing that would be convenient would be to unpack each column into S, I, and R. So maybe we can change the return there to return the transpose of the matrix. So instead of having 3 columns, we have 3 rows, because this is the transpose of the matrix. And now we can unpack the output of the function and have one set of values for S, one for I, and one for R. This is not an important thing, but this is just the kind of small tricks that you can use if it makes your life easier. So sometimes I'll put them in just to let you know that there are lots of different things you can do to simplify your code. Okay, so now we need some way to visualize what we have. We can pack this up into a function that computes the model and then plots it. In general, this is not a very good idea, because you should separate interface aspects from the actual code. But if you're doing something just quickly, a very small program just to visualize the data or experiment and so on, you don't need to worry too much about that. When things start getting complicated, remember to properly decompose your code and organize things, because for more complex programs, that will be very helpful. So, what did I do here? Here we start with creating the time steps we want. So 1000 between 0 and the number of weeks that we require. We compute gamma, so gamma will be computed as a function of the time it takes to recover from the disease, and beta will be computed from the R0, that parameter of the spread of the disease, multiplied by the gamma, or it's the same as dividing by the recover time. And then we compute, do the simulation, create a plot, and plot I with red color, recovered with green, and susceptible with blue. And then we I changed here the values. This should be S and I. I think I changed the legends by mistake, but the idea is to plot each one with a different color, and then I'm going to put the labels and save to a file if you want. So this way we can call our simulation with just one call to the plotting function, and here we have the graph. So you can see here the infected are increasing, and then they start to decrease. They start to decrease because the susceptible population starts to decrease too, so it's harder to infect new people, and then the infected ones start to recover, and since they no longer infect too many people, they start disappearing. And now here we have the recovered, which start increasing. So after say 30-40 weeks, something like that, the disease has gone, and mostly everyone has caught the disease and has recovered. So this is basically what happens if we have these parameters for this kind of disease. We can improve the chart a bit. We can add, for example, let's add an arrow to identify the peak. We have here the peak for those that were infected. This legend is wrong here because I made a mistake, and I switched the order on the labels, but the red one is infected. And the way you can do this arrow is you can create the vector for the arrow. So basically you're going to do an arrow that has 1/10 of the x-axis in width, and then the y-axis divided by 10 million in height. So basically this gives us this inclination here for the arrow. And now we can say what point the arrow is pointing to. So we're going to annotate here at this point, which is the time corresponding to the peak, and the population corresponding to the peak. And this peak is the maximum number of infected. So we are going to point to that the peak of this red curve here, which corresponds to the infected ones. And we can do this by annotating with some text. We set the coordinates, and then we tell what arrow we're going to create. So we have this this arrow drawn here, and the properties of the arrow have this greater than sign at the end, so to specify at which end you're going to put the arrow point. So you can have arrows on both sides, or just have a line, whatever you want. So all these parameters, you should look up the documentation. There's no point in trying to memorize this, but the idea is to show you an example of how you can put these annotations in the graph. So you can do this if you need to annotate something on your graph. Also, the way I'm creating the text here is if the peak is larger than 1 million, then I create this text. So this is an F string. When you precede a string with an F, you can add these curly braces inside the string, and whatever you have inside the curly braces, Python will evaluate. So you can create the string by using variable values inside the string. And these are formatting options. So I'm going to remove the decimal points, use a floating point with no decimal points, and I'm going to, if this is greater than 1 million, I'm going to divide by 1 million and say million infected. Okay, so this should be 2 else. If not, then if it's not greater than 1 million, I divide by 1,000 and say thousands infected. So this would allow this value to change depending on whether they are million or thousand. So basically, this is the kind of details you can do to customize your plots. And now we can experiment with different parameters. So this would be for COVID-19, which has a recovery time of about 2.5 weeks and an R0 of 3. If we change this, for example, for the flu has a recovery time of about half a week, so say 3-4 days, and the R0 is around 1.2. So you can see the difference. The legend is not right, but the colors, the red one are the infected, the green are the recovered, and the blue are the susceptible. So you can see that with these parameters, nearly everyone will get the disease, and we have a very high peak at the time of maximum people infected. But if we have these kinds of parameters, then the peak is much smaller, and only about 1/4 of the people, 1/3, will get the disease. So this way you can simulate different parameters and see the results. So let's adapt this to a slightly different problem, which is chemical reactions. But I say slightly different because even though the problem itself is very different, when we go down to the details of how to model it, it becomes very similar. So let's suppose we have some abstract reaction where we have 2 of A reacting with 1 of B, and this will give us C, and this is an irreversible reaction. So it only goes in this direction, from AB to C. There is no reverse reaction here. So we can compute the rate of the reaction in this direction, or the speed of the reaction if you want, by multiplying the concentrations of all the species involved. So if since there are 2 of A, we get 2 times the concentration of A, so multiplied A by A, and then we have B, and this is the kinetic constant that tells us the velocity of the reaction. So this would be the forward rate, and in general you can just use the quantities or the stoichiometric coefficients there to raise each concentration to that power, and this will give you the rate of the reaction. So if we have a generic reaction with some reactants and some products, we have the forward rate, which will be given by the forward kinetic constant multiplied by each concentration raised to the amount of that species participating in a reaction. But then we have the reverse reaction too, and it's the concentration of the products, each one raised to its own amount, and this multiplied by the kinetic constant in reverse. So in general, chemical reactions, many of them are reversible, and they tend towards an equilibrium where the 2 sides are going at the same rate, and so the sum of these, or these minus that one, will cancel out, and the overall change is 0. Now, if we have the rate of the reaction, we can easily compute the derivative of each species that is reacting. So each reactant, each one on this side, will be consumed by the reaction if it's going forward. So we get minus the rate of the reaction multiplied by the amount, the quantity of that reactant participating in the reaction. Note that if we have the reaction going in reverse because we have too many of the product, then the rate will be negative and this will increase. So the derivative will be positive. And the same thing for the products here. We use the rate of the reaction, we multiply by the amount for each product. For example, P1 is multiplied by this X, but now it's positive because the products are being produced when the reaction is going forward. So let's see how we can model this. We need to create a function for the derivatives, or for the gradient of the overall function of all these variables, but the derivative of each species. And so we'll need to create our function to be compatible with odd int. So we need these two first arguments. First one is a vector with the concentrations of all species at the current time. And the second one is the current time. Once again, we are not going to need the current time because our equations do not change over time. They're always the same expression, but this is something odd int always gives the gradient function, so we need to account for that. And then we're also going to need a few other things in order to be able to generalize this and represent this in general. So we need all the quantities in the reactants, these m, n, and so on. We are going to have a vector so that for each species we have how many of those are in the reactant, so in the left side of the equation. And also we need the quantities for the product. So again, another vector. All these vectors will have the same size, and this one will tell us these concentrations. This one, the quantities in the reactants, will tell us these stoichiometric parameters here on the left side of the equation, and this one for the right side of the equation. Then we need the two constants. We need to know the forward constant for the equation and the reverse constant. Okay, let's see a few examples of how we can test our gradient function. But first we need to write it. This is fairly easy. The overall rate of the reaction is the product of all the concentrations of all the species, with each concentration raised to the amount that species is present in the reactants. So this is something easy to do because this is a numpy vector, this is a numpy vector too, so we can just do element by element this raised, so each element of the concentrations raised to each element of the reactant stoichiometry, and then we just do the product of all of these and multiply by the forward constant. Now here there is another useful trick. I put this in parentheses here at the beginning, and this allows me to break the line and continue on the following line. Python also allows you to do this if you use this backslash, but usually parentheses are better visually and make the code easier to understand. And the reason I did this is because if you look at the code like this, it's harder to see if I'm making any mistakes. It's a lot more confusing. But if I put this, I line these two one bit below the other, I can see that this is the forward rate, so the reactants and the forward constant, and then minus, and this is the reverse, the backwards rate, which is the reverse constant and the products. So this way, if you write your code taking care of making it easier to read, then you can avoid a lot of mistakes. So this is the rate of the equation, and now the derivatives for all our species in the reaction is the rate multiplied by the concentrations of the amounts the products are present in the reaction minus the rate and multiplied by all the amounts of the reactants. So now how can we specify an equation? Suppose we're going to test this with a very simple reaction that just transforms A into B. So we start with concentration 1 of A and 0 of B, and we start at time 0. The time is irrelevant here, but now we specify that we have 1A in the reactants, but we don't have B in the reactants. So this first vector is just 1, 0. This means that there is 1A in the reaction and no B. And this is 0, 1 for the products. So basically, this is a reaction of the type A, it gives B. We have a 1 value for the forward constant and a 0 for the reverse constant. So this is really an irreversible reaction that is transforming A into B. So in the reactants we have 1 of A and 0 of B, and in the products we have 0 of A and 1 of B. So this is the way we can use to specify these amounts so that these expressions work, because when we raise something to 0, that just becomes 1 and it's ignored in the product. So that's the same as not being there in the expression. And now we can test our function. I'm going to omit a lot of tests here, so otherwise we don't have time to cover everything, but I just want you to remember to always test your code. So figure out simple tests that you can do, because if you accumulate errors, then everything becomes a lot harder to solve or to make work. So this would be a good test. We start with 1 of A, 0 of B. We specify this reaction. So A will give B with a constant of 1. And this means that our derivative should be minus 1, 1, because the rate at which A is changing is minus 1, because A is being consumed, and the rate with which B is changing is 1. Now we can model a similar equation here to do another test, which would be an equation of this kind, because we have a forward constant of 1 and backwards constant of 1. So we have the forward and reverse reactions there. And now we can set this at equilibrium. We can have an amount of 0.5 of A and B in, so the concentration in our solution is 0.5 of each. The stoichiometry is the same. There is 1A and 0B in the reactants, and 0A and 1B in the products. So in this case, since this is at equilibrium, the constants are the same and the concentrations are the same, we should have derivatives of 0, and we can check that the two derivatives are 0. So basically, I'm going to be omitting all these tests, but remember, you should always figure out some tests to do to make sure that your functions are working. Okay, so now let's simulate our reaction. We create this function to do the simulation, and this receives the initial concentrations and the specification of what the reaction is like. So which ones are in the reactants and by what amount, which ones are in the products and by what amount, the constants, and also we specify how long we want the simulation to go through. So here we create 1000 points from the beginning to the end of the simulation. This is similar to what we did in that other model, so we can have smooth curves when we draw the plot. And now the result is the integration of this equation. So we're going to use the reaction gradient function we wrote here. We're going to give it these arguments, reactants, products, Kf and Kr, because these are the additional arguments the function needs. And we're going to start with this initial concentration that is provided here. And this is the vector of time points we want to compute the concentrations for. At the end, we're going to return the matrix, the NumPy array with all the concentrations, and also the vector with the times. So this makes it easier then to plot the graphs and so on. For plotting, we can receive the labels, the names of the different species, the concentrations, so all the metrics with the computed concentrations, the axis for the time, which is going to be our x-axis, and if we want to save to a file, we can get the file name and save it to a file. So this would be easy. We just create a new plot, and for each label, we're going to plot that column of the concentrations. So in this case, we need the labels, which are the names of the species, and we also need to know which column they correspond to. So we can use the Enumerate generator here that will give us both the index and the value of this set. So with index 0, the first label, with index 1, the second label, and so on. This way we can match each label to the appropriate column on the concentrations and do the plot. then we just put the axis labels and the legend here. Now this I show you a slight detail here on the legend. If we plot the graphs like this, you see that there are these white lines in the graph. So in order to avoid having white lines on the legend itself, what I did is to create a legend where I write the frame of the legend, so the area where the labels appear. I write it opaque, so alpha is 1, this is the opacity, and the color I assign to it is the face color of the plot, the axis here. So the face color of the axis is this background color in this place. So I'm going to, from plot, get the current axis, and the current axis I get the face color, and I set the same color there. So if you want to customize your legend, this is just a simple example. There are lots of different options that you can use, but just to let you know that you don't need to have always the default legend. If you want to do some slight touch-ups, you can look up the documentation and see what options you have. Okay, so this is what we can do now. We have these labels A, B, C. So we have this reaction here, which is 2 of A plus B will reversibly be converted to C. And this is what we are describing here. So we always have A, B, C. These are our 3 species. But in the reactants, we have 2 of A, 1 of B, and 0 of C. And in the products, we have 0 of A, 0 of B, and 1 of C. So that's how we can describe this reaction here. And then we are going to simulate using these initial concentrations. So we start with 1 of A, half of B, and 0 of C. We have these constants. The forward constant is 1, the reverse constant is 0.2, and we simulate everything up to 10 time units, for example, 10 seconds if you have everything in seconds. So this is what we get as a result. A is being consumed, B is also being consumed, and eventually the reactions even out, so forwards and backwards, and we reach equilibrium and everything stops. Now, one thing that is not very practical is to have to send all of these different arguments here and carry all these different variables at the same time. So if you start doing things that have lots of arguments and these start to become a bit complicated, then one thing that you can use, which is a very useful thing in Python in these cases, is to create a dictionary with all your arguments. You can either create your dictionary in the usual way, so curly brackets and some key, for example, concentrations, and then colon and so on, or you can just call the dict constructor with named arguments corresponding to your keys. So if your keys are all strings, you can do this like this. So this would be a string const I with this array, kf with this one, and so on. And we create a dictionary with all the arguments we're going to need to give to our function. And now the advantage of this is that if you call a function with a dictionary and add 2 stars before the dictionary, this will be unpacked into all the parameters with the names corresponding to the keys of the dictionary. So if your dictionary has as keys all the parameters you need, you just need to send the dictionary like this, and this works. So why is this useful? Because if you have lots of different parameters and just want to change one, you don't need to be doing this kind of thing all the time, or remembering if you changed one before, or in which line of code you have one or the other. You can just do something like this. So I take the reverse kinetic constant and I set it to 0. Everything else is the same, and now I just run the simulation, keeping everything else the same, but without the reverse reaction. So you can see the difference here. If we have a reverse reaction, we reach an equilibrium. If we don't have, if we put it, create an irreversible reaction, now everything is starting to tend towards 0 on the reactants and reaching the fixed value there on the product. And we can also change, for example, let's change the forward kinetic constant, which initially was 1 when we created here, but now we keep everything the same. So the reverse one is at 0, stays at 0. The forward one we increase to 2, and now we can see how the plots change. So let's see an example of complicating this a bit more, where we can extend this easily into several simultaneous reactions. So what we did here was to solve for one reaction. Now we're going to solve for a set of reactions that are taking place concurrently. So what we need to do is we need to have all the species for all the reactions. In this case, let's assume that we have an enzyme, a substrate, the enzyme can bind to the substrate, and then there is a catalysis reaction that recovers the unbound enzyme and produces the product. So these are two reactions, one that is reversible here, and then an irreversible one with the catalysis. So we need to create all these reactant and product amounts for each reaction, and also the constants, forward and reverse. The concentrations, however, are the same for all reactions. So here we have these species, E, S, and P. So we have these 4 different species, and we will always use the same 4 concentrations for all reactions. So let's see how we can do this. The way we can model this set of reactions is by using the concentrations as 4 values, because it corresponds to the 4 species. We're going to start with a tiny amount of enzyme, a lot of substrate, and 0 of the bound complex and the product. And then we need 2 forward constants, because we have this reaction here, the first one, and then we have the second reaction. So we're going to create 2 forward constants. The first one is 400, so this binding is very fast, and then we have the catalysis with a 40 catalysis rate here. So these are arbitrary units, but just to give an idea of the proportions. Now we have the reverse constants. This is for this equilibrium here, the first one, and the second one is 0 because the second reaction is irreversible. And here we describe the shape of these reactions. So E plus S gives ES, means that in the reactants there is E, there is S, there is no ES and no P. And in the products of this first reaction, we have no E, no S, 1 ES, and no P. So this is what's happening here. And now for the products, we have for the products of both reactions. Oh, sorry, this is the reactant for the second one. So this is actually this part, but it's as the reactant on this second reaction. And now for the products on both reactions, we have this again, because this ES is both the reactant of the first reaction, the reactant of the first reaction, and the product of the reactant of the second reaction, and the product of the first reaction. And we have the same thing to describe these here. So in this case, we have E and PS products, 1, 0, 0, 1, and for the first reaction, we have ES as a product. So by creating these matrices with the stoichiometric coefficients and putting a 0 where we do not have a species, we can specify whatever set of reactions we want. But now we need some function that can take this and compute the derivatives. We're going to make use of the previous function, the reaction gradient, that could compute the derivative for a single reaction. And what we're going to do is to start the derivatives at 0, and then go through all the reactions. For example, we can take the length of one of these vectors, or the shape of these matrices. It's all the same because they should all have the compatible dimensions. But we're going to loop through all the reactions, and for each reaction we're going to use the reaction gradient function we had before to compute the derivatives for that reaction. So we're going to take this row of the reactants matrix, this row of the products matrix, this forward constant, and this reverse constant. And we're always using the same concentration. So we are frozen in time now and looking at what the different reactions are doing and adding all their effects. So we start at 0 and then we add all the derivatives. And this allows us to extend our program to use multiple reactions just by reusing the previous function and putting it into a loop to add all the derivatives. Okay, so now we have an additional small problem, which is how we're going to use this function in our simulation. So when we wrote the simulate reaction function, we called the reaction gradient function. This was fixed in our code. But we can do a slight change to this function. We are going to add a default parameter here. So this grad parameter by default is the reaction grad function we created first. And our simulate reaction will use that function by default. So this way, if it's called with only these arguments, it will still work the same as before. That it's a slightly different version, but we have the reaction grad here in this variable, and then we call this variable, so it works the same. However, there is now an additional argument that we can provide if we want to give this function a different gradient function. For example, to allow it to use multiple reactions. So this is another trick that you can use if you want to change your code in a way that doesn't affect the previous usage, but allows you to have more functionalities. You can add parameters that have default values in a way that keeps everything the same if those parameters are not being used. So all your old code should work the same, but now your new code can use this new functionality on these functions. Okay, so let's specify this reaction. We create a dictionary with the reactants for the first reaction, the reactants for the second reaction, and then the products for the first and the second, and all these constants. Now we can simulate everything and we get this plot. So basically what we have here is we have the product being generated, the substrate being consumed, and here below we have the enzyme being bound to the substrate, but this is almost invisible here because the enzyme has only a small amount there in our solution. But we can complicate things more. For example, here we have 4 different reactions. The enzyme binds to a substrate, it can produce the product, it can bind to an additional substrate molecule and produce the product, and the same enzyme bound to one substrate molecule. So we have 4 reactions here. We specify the reactants, the products, we give all the different constants, and then we can just plug it into the same simulator. We have the simulation here. Now we have more species. And if we want to look into detail on only a few species, we can do this. So we can call our plot model function, but we are going to use only the first, the third, and the fourth species in our set of reactions. So only this one, and this one. These are all the ones that involve the enzyme. So now you can see that the scale here goes up to 10 for concentration, but if we look only at these, we are looking only at this line here, and we see how the enzyme and the enzyme complexes change. So our enzyme starts free, but quickly goes down. The free enzyme goes down to 0 as everything binds to the substrate. So you see this rise here right at the beginning of the reaction, and nearly all the enzyme is bound to 2 molecules of the substrate. So you have here a steady state where things are being produced, but eventually when we reach around here 40 time units, then the substrate has decreased a lot, and now we start having unbound enzyme. We start also having a bit of this green one, the intermediate one. So basically with this modeling, we can take a look at what's happening inside the reactions. Okay, so now let's suppose we want to fit our model to the data. I'm just going to look at a very simple example, and we're going to use data from Direção-Geral de Saúde. This is recent data here in Portugal in the COVID-19 disease, and this is the number of infected cases, so confirmed cases by PCR testing. So this is since the beginning of registration. We are now around 100 days after the beginning, but we can see that we have this exponential stage here. So let's select this part up to 5,000 cases where the curve seems to be approximately exponential. One easy way of plotting this, we have this CSV file with lots of data, but one of the columns called confirmados has the total number of positive tests. So if you want to just take a look at what the data looks like, it's very easy to do that with pandas. You read the CSV from the file into a data frame, and now you just say, I want this column and plot it. And if you do this, you just get the plot immediately. So this is very simple, very easy to use, just to start examining the data. Okay, so selecting those with more than 10 and less than 5,000 cases, so the days which have at least 10 confirmed cases and up to 5,000, it's easy. We're going to copy the create this conf variable with the column of the confirmados. This sometimes it's a copy, sometimes it's not. If you want to make sure it's a copy, you can do something like this. You can add the copy here, but in this case it makes no difference because we are not going to change the data. So Pandas sometimes optimizes this, and instead of copying the data, just gives you so to speak, a window, a view into the original data. So now we have the column here, and we can say I only want those with more than 10 or at least 10 and no more than 5,000. And we can create this Boolean series. We saw this previously. This is a Pandas series, so we can compare with the value and create a Boolean series. But we can use this symbol, the commercial and here, to do the conjunction between the two. So it's confirmados greater at least 10 and confirmados at most 5,000. So we get this set of values here, and we can now plot it to see the exponential curve. Okay, so now let's fit this to an exponential model that is something like this. The population at time t will be the population at time 0 multiplied by some beta parameter raised to time t. So this is the exponential part. Time is there on the exponent. We're going to use this function from SciPy, curve fit, that receives a function that gives you a y vector given an x vector. So it will feed the x into the function, obtain a y, and compare to the target y that we're going to fit it. And then it will adjust the parameter in a way that minimizes the quadratic difference between the target and the output of the function. So we need a function of this shape, of this type, where we receive the x values and the parameters that we're going to change, and we output the y values that curve fit is going to compare with the target. So this works a bit like solve in Excel. Since we're going to use other values here, we're going to look at the population and so on, we can use a local function to access these other values. So let's import the curve fit first from SciPy optimize and see how we can solve this here. So this function is the exponential function that outputs these values. So we take the initial population and we multiply it by beta raised to each time value. So the time will be the x here. This will be a vector with all the time, the days after the beginning of the epidemic, and we use this as the exponent here. So beta raised to the first day, the second day, and so on, and we get all the values here. And this is the initial population, so the 10 people who started infected in our selection here. Now, one problem here is that curve fit will call our function exponential, we'll give it the times there in the first argument, and the parameter we want to optimize as the second argument. But we don't have access to the initial population. One simple way of solving this is to write our exponential function as a local function inside the function that does all the fitting. So what this means is that this function also has access to names that are in the scope of the parent function. For example, this beta name, when Python wants to evaluate here, it will find that there is a local variable called beta. So it will not look at this one, it will look at the one that is being given to the function. But when it goes for pop0, there is no pop0 here in the local namespace. It will look in the enclosing namespace of the parent function here. So it will find this one and it will use that one. So in some cases, it's useful to have a function that can peek into the values of the other function, and you can do that by creating it as a local function. It works locally as the other variables. It has no existence outside the parent function, but it can do these kind of tricks here inside. Okay, so we start with an initial guess of our beta as 1 here. We start with the population, initial population being the first value on our target values, so basically this set of values that we selected. And we create a set of times that is just from the first moment to the end. So we just use a range. The first day is day 0, the second day is day 1, and so on, all of these days. Now we call the curve fit, and curve fit returns 2 values. First, it returns an array with the parameters that it found that optimize the adjustment between the output of this function and the target values. And the second parameter is the covariance of these arrays, which we will ignore for this purpose, so I just put an underscore there. And since this is an array, but we only want one value because beta is the only parameter we want, we'll just return beta, which is the only element of this array. So what this does is it's going to change this beta here until the output of this function is as close as possible to the target values. And the target values we receive there, and now we can put this all together. So we read the CSV file, we get the confirmados column, we select that exponential stage, which is between 10 and 5,000 approximately. We get the values from these series. So remember this, when you select from data frames and series, you get series, they have these indexes. But if you want to just have the vector, the NumPy array with the values, you can use the values attribute there. And now we're going to fit the exponential curve, and then we're going to plot it. We're going to create an x-axis from 0 to how many data points we have selected there. We're going to create the y values that is the starts with the initial population, but then just is the beta value raised to each day, each value of the day. So this is the exponential curve there, but now using the beta that was optimized by fitting the data. And now we plot the data points with circles and a line for our fitted model. So let's take a look at how this looks like. We have the data points here, the fitted model here, and then we have this legend. And notice that I put a beta there with the value. And the way I can do this is to use LaTeX commands here. So I use this $sign for the equation. I put the beta there, and then I also use this inside of an F string so that I can insert the actual value of the variable with 2 decimal places. So if you know a bit of LaTeX, you can format your legends and titles and so on, and include equations, include these kinds of expressions in your plot. Okay, so I'm running a bit over the time, sorry for that, and I will compensate in the second lecture. So what we saw now is using SciPy for 2 things. Numerical integration of dynamic systems. This is very common when you're dealing with lots of different models. So basically anything that evolves over time, it's possible that you can have some model to describe your problem using differential equations. So with this numerical equation package, numerical integration package, you can easily write your models and see how it works. And then you also, if you have mathematical models of whatever phenomena you're working with, you can fit parameters of your models so that you adjust to the data you have and can compute these parameters. We'll see other ways of doing this, 2 other functions, but this one, for starters, curve fit, is a very simple one to use. It minimizes the quadratic error between the predictions and the data you have. And also I gave a few more examples here of visualization. I'm going to do the same after the break, give a few more examples, but these are not exhaustive. They're just to call your attention to the fact that you have here in Python, in Pandas, PyPlot, and so on, you have lots of tools for visualization, and if you spend a bit of time looking at what they can do, you can really show your data and your models much better than what you would do, for example, using Excel or something like that. Okay, so let's take a small break. We continue at 6:15, so in about 10 minutes with the second part. See you soon.